Hello everybody, in this video I will create a tutorial for a library known as DeepChem. So this library is very helpful if you're trying to solve problems related to life sciences, chemistry or biochemistry. So I'm basing this tutorial on this fantastic book, Deep Learning for Life Sciences. I would highly recommend anybody who is into deep learning in life sciences or deep learning in biochemistry or chemistry related problems. This would be a fantastic starting point. And this is a nicely written books. So I will be making this tutorial on the toxicity datasets. This datasets is openly available. So this DeepChem is fantastic in terms of collecting datasets. So they have a huge collection of datasets that you can take advantage of it, and it's kind of pretty nice. So let's begin this tutorial. So let's import. Let's begin this by importing. Come on. Import DeepChem as DC and import NumPy as NP. So DeepChem is built upon TensorFlow. So you will need to install TensorFlow to use it. And also for some of the functions, I think it needs PyTorch as well. So I'm working in Conda environment. In my Conda environment, I have Python, TensorFlow, DeepChem, and also you need RDKit. RDKit is a popular package, popular library that's to interpret chemistry structures. So that's kind of a critical one. So you should have RDKit if you want to take advantage of DeepChem packages. I'll post the link how to install. I used simple pip install, DeepChem, pip install, NumPy. You can do using Conda as well. So let's load our data sets. Okay, let's load our data sets by task datasets and transformers. I'll explain what each one of these means. So like I said, DC does have a lot of data sets. One of these data sets is MolNet. So this has a huge number of data sets that you can import directly from our DeepChem packages. So today we're going to be using Tox21 data sets. So this will get your data sets from the Toxicology in 21st Century Initiative. So this is where it's getting the data sets from. A few things I want to highlight. One thing is in all of these data sets, there is something called featureizer. So what this is doing is it's featureizing or vectorizing each molecule. So in this case, we are using ECFP, but there are a bunch of other featureizing method also present in DeepChem. So ECFP stands for Extended Connectivity Fingerprinting. And next important thing that you want to pay attention is transformers. So a lot of these data sets has a transformer. So this one is using a balancing transformers. So what this does is it's ideal for imbalanced data, right? So for example, let's say we have a very small number of data sets, maybe let's say you have 99% of the data sets has a positive values and only 1% of the data has negative values. So in that case, if you try to train a neural network, the model will basically say, you know what, I gave up. I will just say 99% of the time is what was I said, positive. So let's say 99% is positive. I'm just gonna say every time positive. It doesn't matter. I don't care if it's positive or negative. I'll just keep saying positive. Then your model will be 99% accurate. So that's not correct, right? So we have to optimize those things. Okay, so those are the few things. One was featureizing aspect and also the transformers. So let's load. So you can see here, if I put task, so basically we got this 12 tasks. So you can see the length of the task as well. So we got 12 tasks. what are these tasks are. So again, so these tasks are, these are 12 biological assays upon which each molecule is being tested. So we are trying to see which of these assays where it's binding to create a toxic impact. So these are the 12 assays that's going to have some values for each one of this molecule. Now this is not a simple classification problem where you have a picture where the picture could be cat, dog, elephant, or giraffe. So it has to be only one of the all the categories, right? So a picture cannot be cat or a dog simultaneously. But here, this is a multi task classification problem. So in this case, a single molecule can be active here, can be active here, can be active here, can be active in all 12 of them, or it can be inactive in all 12 of them. So that's a different classification problem that you commonly encounter in image classification problems. Okay, so let's move on. These are our tasks. So these are the assays, 12 assays. Let's look at our data sets. Let's split our data sets into train, valid, and test. Maybe we can call it test data sets, valid data sets, and training data sets. And data sets. So now let's look at their shape of each one of them. So print, I'm just going to start with train ds.shape. Okay, so each one of these data sets has split it into three variables, x, y, and w. So x is obviously our input. I'm just gonna draw all of them. So y variables are the variables related to our 12 assays. And the last thing that we have here is the weight variable. Now let me explain what this is. Okay, so let's look at the shape of each one of them. So you can see we have in total in our training data set 6,264 molecules. Our x variable has 1024 inputs. So 1024 characteristics. So what does this mean? So this is something that we derived from remember when we talked about when we are loading this data set, there was something called featureizer. So it featurized molecule via ECFP, and that ECFP provided 1024 properties for each molecules. So these are those characteristics of each molecule, 1024. This is what we will be training on. And then look at this Y data sets here. So this Y data sets has a shape of same 6,264 molecules, but it has on the other dimensions, it has 12 outputs. So that's basically this 12 task. So this 12 stands for data for 12 tasks. It is active, inactive. All right. And the last one is the weight variable. So the weight here gives us a specific weight number that has to be multiplied when you are training model. So this weight is, so a lot of the time, the molecule that's here, like the researchers, when they created this data set, they did not test across all these targets. So some of the data sets were empty, but you cannot leave them empty. So what they did was there was a bunch of zeros in there. Like if the data sets, if out of 6,264 molecules, some of them are not tested against some of the target, then the weight, we don't want to consider those. So the weight is there as well to take care of this one. So we can find those things out by doing something called np.count non-zero. And let's look at the non-zero, how many non-zeros we got here. train.ds.w. So see here, 63,647 are non-zeros there. So if you multiply this, let's say 6,264, that's how much we got, and multiplied, that's how much we have here, and multiplied by 12. and you see 75,168. So technically you should have 75,168 non-zero values there, but it turns out some of them did not have enough data, so we just packed them. Well, not we, the people who did this, created this data set, they packed them with a bunch of zeros. So that's pretty much what we have here. All right, so that's about understanding data sets. And you can look at the transformers. The transformers, if you click transformers here, you can see the transformer that's used is called balancing transformers. So it's create the data sets in a much balanced way with proper weight is there. That's pretty much, oh, okay. So let me print out the shape of the test data sets. So we can print it out, test data sets dot x variable for the test data sets shape, and we can have test data sets y variable dot shape. We also can have the w variable, the weight variable. Okay, so you see in our testing sample, we only got 784 molecules. Here 6,200, and 784. All right, so that's all we have about the data sets, about how we can see it. Okay, let's try to go and build a model. So let's create a model object just like any other neural network. So we're gonna use the models function, dc.models. This time we're gonna be using something called multitask classifier. So this one is the one that gonna help us classify. Remember we said each molecule can be active on not just one but multiple of this task. So that's why we're gonna use the multitask classifiers. Okay, so let's look more detail into what we can enter here. So first things first important. So we are trying to build a much simpler model here. But first, most important thing that you have to put is n task. So how many tasks we have here? So we have here 12 tasks that represents the 12 assays right here. Okay, so next critical thing that we need is n features. So how many features we have for each molecules? Well, our number of feature was 1024 because that's how many that's what the shape of the X data sets tell us. Okay, so that's how many features we have. This is what we'll be training on. So these are the properties derived for each molecule by the ECFP featureizers. Okay, next important thing that you want to do is layer sizes. Now here layer sizes, you can decide, it's up to you. You have to optimize based on this. So layer sizes is basically tells us what is the width of your neural networks. So in your hidden layer. So if you look at your neurons, so we got neurons. So how many neurons you want to have in your hidden layer? So let's say I want to have one hidden layer with 500 neurons in it. So that's gonna, I will put, and then the output will be 12. But what if I want two hidden layer? In hidden layer 2, I want another 500. Then they're all gonna be connected hidden layers. So if you want put 1000, again, 3 hidden layer, it's up to you, but you can keep going on as many as you can. It's gonna be computing intensive. So I will keep it simple. Maybe I'll just do 1000 and 1000. Let's just do one so that it will be faster. Okay, so maybe make it slightly bigger, maybe 1500. You can play around with it, see which works the best for you. Next, you wanna keep in mind is dropouts. So dropouts are kind of handy ways to stop. So it's randomly drop 50% of the neurons. So it's kind of nice way to stop overfitting your model. It's by default 0.5. If you want to change it, feel free to change it. Maybe you can change it to Let's not change it. Let's keep it default. Yep. So if you want to change it, feel free to change it. I think that's pretty much the most important ones that you would like to have at least in your out of the box model. So let's look at here. So this is our model. So we have our model. So let's try to fit it. So model.fit, and we're going to be using our training data sets. And so you're going to pass batch by batch. So the epochs is basically telling us how many times you want to pass your data sets through this model. Again, this is something you can play around with it. I have seen 8, somewhere between 5 to 20 works good. So let's put 10 in there, 10 epochs, that's by default everybody uses. So this means your entire data sets will pass 10 times, and then the gradient descent will try to optimize the loss and try to predict the best model. Okay, so let's do this. It will take a couple of seconds. It's not that compute intensive. Okay, so our loss turns out to be, so if you notice this one, its output was the average loss over, so the output at 0.477, it's gonna be an average loss over the most recent checkpoint interval. So that's 0.47. So it's pretty, seems pretty good. Might be overfitting the model. So let's evaluate our model. Okay, so we can evaluate, it has a bunch of wrappers. DeepChem has a bunch of wrappers that can wrap around a common metrics method. So I will use, this is one good method to use for this is ROCAUC score. Dang, this is a difficult word to pronounce for me. Okay, so we can use ROCAUC score for this. Matrix dot dc.matrix.ROCAUC score, and we want to find out when we present, we want to find out ROCAUC score for all the 12 tasks, and we want to find out the mean of ROCAUC score. So basically what this tells us, the ROCAUC score is the model will output random numbers, but we gotta tell them, is it the molecule is active towards a target or not active. So you want to binarize this. So the ROCAUC score is a good way to do it. So it basically tells us a threshold value. What is a good threshold values for your curve? So for example, let's say you gave a very tough exam and only 3 students score above 60. So if you put your passing score as 60, that means only 3 students will pass and the rest of the 97 students will fail. Okay, so in that scenario, is it a good metrics for your entire class? So think about this way. Only 3 students pass, 97 students fail, but all of those 97 students, some deserve to fail, but most of them didn't deserve to fail. So what you want to do is you want to optimize that threshold in a way so that a lot more deserving students will pass. So maybe I'll change the passing score to 40. Now 80% of the students are passing and 20% of the students who didn't study, they are failing. So you get the idea of it. So number of false positive will number of false negative will go up if you put the threshold too high. So if you set up a tough exam and then threshold is too high, the number of students who didn't deserve to fail will fail. So your false negative is gonna go up pretty high. But on the other side, if you have, let's say you set up the threshold too low, maybe you put the 10 as a passing score, then everyone is passing. There are gonna be a lot of students who didn't study, didn't deserve to pass, but they are passing because you have a lower threshold. So you are increasing the false positive rate in that scenario. So this is where the ROC AUC score comes into play. So what this is doing is the ROC AUC score, it's gonna plot a data between false positive and true positive. So it's gonna plot a data between false positive rate and true positive rate. So so that's gonna that curve is gonna be somewhere between 1 to 0.5. So if it's perfect in a perfect environment, what do you call the perfect threshold, where all the deserving candidate pass, all the non-deserving candidate fail, then that environment would be 1. But if you're randomly predicting, that would be 0.5. So if it is in between 0.7, then that's good. 0.5, so the number could be 0.5 to 1. Okay, I think I did enough rambling. I think if you want to know more about ROC AUC score, I would highly recommend the YouTube channel, the Stats Quest guy. He does fantastic explaining the statistics of all the numbers. Okay, so this is our things. Okay, now we let's evaluate our model. So we have train scores. Let's call this train scores is model.evaluate, and you want to evaluate your training data sets, and you want to use the matrix here, the matrix function that object that we created, and the transformers is going to be the transformers that we had here. The transformers right here. So that's our transformers. And let's print our training score. So our training score is 95%. So it's really close to 1, but let's not too excited about it. This is from our training data set. So model is definitely overfitting. Let's hold our breath for our testing score. I doubt it's gonna be that high. Well, not doubt, I'm confident it's not gonna be that high. So model.evaluate, and this time I will use the test data sets. And we want to use the same metrics. You can here provide a bunch of other metrics as well, like whatever you want to measure. But this is a better method. Okay, print test score. Okay, 68. Oh, dang it. It dropped. Last time I did, it was like 69 or something. That would have been fun. Okay, anyways, so you see our model is definitely overfitting, but it is doing 68% on our test score. So it's like if it had been like randomly guessing, then that would have been 50%. 50% is worse. So now we are doing like 18 out of 50, so roughly 20 out of 50. So we are doing 40% better than just randomly guessing. So we could optimize this model again by adding more layer sizes or increasing the ECFE featureations. Instead of 1024, you want more features there, more vectors in there. You could do more epochs. I don't think more epochs will help. So you could do a bunch of different things to optimize this, but this is just a simple model that's out of the box, which is doing much better than just simple randomly guessing. Okay, yeah, that's all about this DeepChem. So I'll create more video on this DeepChem library and the RDKit library, so stay tuned.